Hi everyone, welcome back. In this video, we're going to build this live Uniswap version 2 simulation from scratch in HoloBit, and we'll focus on its core mechanism, an automated market maker, AMM. At the core of an AMM is a simple but powerful pricing rule. X times Y equals K. This is the constant product mechanism. It keeps the product of the two token reserves in the pool constant. By the end, you'll have a runnable model of an AMM that you can tweak, extend, or fork into your own experiments. This is part 1 of a short series. Here we focus only on the swap side, a DEX agent that quotes a price and executes swaps. In part 2, we'll add liquidity providers on top of the same model. Before we start building, let's share a modeling mindset we'll use a lot. You can think of the protocol, the DEX, and the traders as a game and its players. In this analogy, the game world provides services, and the players send requests. That also gives us a natural modeling order. First, we build the game world, the DEX, and only then do we let the players, the traders, interact with it. Based on this idea, we can quickly map familiar DeFi concepts onto HoloBit components. The DEX protocol is modeled as a passive or reactive agent that waits for users to interact with it. Traders and other users are modeled as active agents that proactively send swap requests. Starting from this mapping, we'll build the smallest possible DEX model. Let's start with the DEX, which we treat as a passive agent. The DEX does not initiate actions by itself. It simply holds its state variables and follows a set of response rules. In the model, we represent its state with variables and containers. For a minimal DEX, we only need to care about 3 things. First, the trading pair name, for example ETH and USDC. Next, a liquidity pool that holds the reserves of the two tokens that can be swapped. Third, a feeRate, the trading fee that a trader pays when they swap tokens. The response rules are defined as processes of the DEX agent. According to the design of Uniswap, a swap on the DEX mainly involves 2 core behaviors. When a trader wants to swap token A for token B, the DEX first needs to quote how much token B they will receive. This is the getAmountOut behavior. Once the trader confirms, the DEX needs to actually execute the swap. This is the swapIn behavior, so we can quickly sketch the DEX architecture as follows. We create a new agent and name it DEX. We add 2 variables, one called pairName for the trading pair name, and one called feeRate for the trading fee. We add a container called liqPool. This container will hold the reserves of the tokens in the liquidity pool. Then we add 2 processes, the quoting process, getAmountOut, and the actual swap process, swapIn. Modeling is not just about making the system run. We also want to verify and understand its behavior. To do that, we add 2 observed variables for the DEX, K and price. K represents X times Y, the product of the 2 reserves. In theory, for each trade, before and after the swap, this product should remain constant. Price is the price of the pair, the exchange rate between token A and token B. Once these variables are set, we can use HoloBit's auto-charting feature to create charts that track how K and price evolve during the simulation. Finally, we can enter the DEX canvas and use the auto-layout function to tidy up the components. At this point, the minimal architecture for a DEX is in place. You can also give the DEX agent an avatar or logo and choose a pink color so that different agent types are visually easy to distinguish. Now let's look at the trader. A trader is like a player in the game. Their core piece of state is their wallet, which stores the tokens they hold. Their key behavior is a process that sends a swap request to the DEX. We can build a trader agent quickly. Drag a new agent and call it Trader. Next, add a container called Trader Wallet. This container acts as the trader's wallet. Then we add a process called goSwapIn. This will be the action where the trader initiates a swap. With just these parts, the minimal trader is complete. To make the model easier to read, we can also draw an annotation line from the trader's goSwapIn process to the DEX's swapIn process. This annotation line is only for visualization and understanding. You may have noticed that both the trader's wallet and the DEX's liquidity pool are modeled using the container component. This is a modeling choice. In HoloBit, containers are designed to store things like assets or resources. They work especially well when you need to simulate deposits, withdrawals, and exchanges. In principle, you could also use variables to model these. But here we purposely use containers both because they fit the use case and because we want to introduce containers as a new concept to you. Now let's take a concrete scenario and fully configure the agent's properties and behaviors so that our model can actually run. We'll start from the DEX and set up the game world first. Let's look at the core properties of the DEX agent. First, set the DEX agent type to population with an initial number of 1. In this minimal model, we only simulate one trading pair. Second, set pairName to be a list. Give it a text initial value, a list containing ETH and USDC. For this trading pair, pairName index 0 is always ETH. pairName index 1 is always USDC. Next, let's look at liqPool. A container is like a small dictionary from name to amount. The keys are strings, the item names. The values are numbers, the reserves. Set the container keys to ETH and USDC. Then open the details configuration and add 2 rows. In the first row, choose ETH as the key and set the amount to 1,000. In the second row, choose USDC as the key and set the amount to 3.7 million. Make sure both entries are configured as non-negative and with no capacity limit. Last, configure the fee rate. In Uniswap version 2, the fee rate is uniform. Set fee rate to 0.003 as the initial value. Now we come to the observed data. For variable k and set its initial value. To the product of the initial reserves, 1,000 times 3.7 million. For variable price, set it as a dictionary. Add 2 keys, ETH and USDC. Set their initial values based on the reserve ratio. The initial price of ETH in USDC is 3.7 million divided by 1,000. The initial price of USDC in ETH is 1,000 divided by 3.7 million. You can switch these variables and containers into monitor mode so that in later steps you can easily watch how they change as the model runs. At this point, the DEX properties and observed data are fully configured. Next, we configure the DEX behaviors. We will follow a calculate first, then execute pattern. First, we set up getAmountOut, then we let swapIn call it. Let's start with getAmountOut. Hover your mouse over the process and click the focus icon that appears in the lower right corner. This will take you directly to the DEX canvas and center on this process. This behavior is purely a calculation. We first set up the input and output ports, then use them to compute how many output tokens the trader can receive. You can think of a port as a small data connector. Whoever calls the process puts values into input ports, and the process returns a result on the output port. Now let's recall the constant product rule, x times y equals k. From this rule, we'll get a formula to compute the amount of output tokens. It tells us which numbers we need and what to put in the compute component. This process takes 3 inputs and returns 1 output. On the right-hand property panel, open the Ports drop-down. You'll see separate sections for inputs and outputs. In the Inputs section, click the Add button and add 3 variable ports with clear names. AmountIn, the amount of input token the trader is sending in, Reserve A and Reserve B, the current reserves of the 2 tokens in the pool. In the Output section, add 1 variable port and give it a clear name. AmountOut, the amount of output token the trader will receive. All 4 ports are numeric, so you don't need to change their type. Here, we won't set default values for the ports. The caller will provide the numbers at runtime. Once you've done that, you'll see small icons appear on the process box, 3 green icons on top for inputs, and 1 red icon at the bottom for the output. The feeRate variable is already defined on the DEX agent, so the process can access it directly, and we don't need a separate port for it. Now we define the behavior logic. After the start event, add a compute component and an end event. These 2 components are enough for the whole process. The configuration has 2 key parts: how the process starts and the formula inside the compute component. For the start event, the default passive trigger is fine. We don't need to change it. In the compute component, set the formula for amountout. Remember to write the formula using this process's port names and this agent's variable names, rather than X, Y, or delta terms. For teaching simplicity, we ignore implementation details like integer rounding. At this point, the how much can be swapped out calculation is ready. Now go back to the swapIn process and configure the actual swap execution logic. Again, we first decide which ports it needs, and then we define the behavior. For swapIn to run correctly, it needs a few key pieces of information from the trader. It needs to know how many tokens the trader is sending in, which token the trader is sending, which token they want to receive, and which wallet should send the input tokens and receive the output tokens. We set these as input ports so that the trader, when calling this process, can pass in the data. For the first 3 pieces of data, we create variable ports AmountIn as a number and token A and token B as strings. For the trader's wallet, we create a container port called Trader Wallet. This port does not have a simple default value. Later, the trader will connect their own wallet object to this port, effectively authorizing the swapIn process to operate on it. SwapIn also needs to send the final amount out back to the trader, so we add an output port called amountout. Now the ports for swapIn are fully configured. Next, let's configure the components inside the process. The logic of swapIn can be broken into 3 clear steps. Quote, swap, bookkeeping. When the DEX receives a request from a trader, it first calls getAmountOut to compute amountout. Then, using a container operate component, it actually moves tokens between the pool and the trader's wallet. Finally, it updates its own state and observed data. Inside the process, add a call component to call getAmountOut, a container operate component to handle the token transfers, and an end event to close the process. Now we configure the details. First, start event, passive, waits for calls. Second, we wire up the call component. Set the owner to self, and choose the getAmountOut process as the target behavior. Now we need to pass the correct values into its input ports. For AmountIn, input AmountIn. SwapIn's AmountIn receives the value from the trader, and then passes it to getAmountOut's AmountIn. For Reserve A and Reserve B, we read directly from the liquidity pool. For Reserve A, we use the amount of token A in the pool. For Reserve B, we use the amount of token B in the pool. SwapIn also has an output port. In the after action formula on the call component, set amountout equal to this dot amountout. This copies the result computed by getAmountOut into swapIn's own amountout port. Remember, only when the ports are passed correctly. Will you get correct results? Now let's configure the container operate, which is the critical step where assets are actually moved. You can think of Container Operate as a logistics center. It connects containers with directed flows, and on each flow you specify what item is moving, the key, and how much is moving, the amount. So a container operation can be read as a set of precise instructions, from where to where, what token, and how much. We first decide from where and to where. Drag a reference to liqPool from the left panel into the process. Operating on this reference is equivalent to operating on the actual data object. Then drag a reference from the Trader wallet port into the process. This port receives a wallet object from the trader. We can't create a direct reference in advance because of scoping rules, but we can operate on the object once it is passed into the port. Now define two flow directions. For the incoming path, tokens flow from the trader's wallet into the pool. Connect the chain. Starts from trader wallet, through the container operate, then into liqPool. This path moves token A from the user's wallet into the pool. For the outgoing path, tokens flow from the pool back to the wallet. Connect the chain, starts from liqPool through the container operate, then into trader wallet. This path moves token B from the pool into the trader's wallet. Once both directions are linked, the container operate automatically turns on exchange mode. This means the downstream amount can be set to auto and will be taken from the upstream flow. We call these four connections container operate connectors. Now set the specific key and amount for each connector. On the incoming path, from the trader wallet to the container operate, set the key to token A and the amount to amountin. From the container operate to liqPool, keep the same key, and set the amount to auto. On the outgoing path from liqPool to the container operate, set the key to token B and the amount to amountout. From the container operate back to the trader wallet, again keep the same key and set the amount to auto. At this point, swapIn can actually execute swaps and move tokens between the pool and the trader's wallet. The last step is to update our statistics. In the after action formula area of the container operate component, add the update formulas for price and K. The first updates the price for pairName index 0. The second updates the price for pairName index 1, and the third updates the value of K. You might ask why we don't just write liqPool of ETH times liqPool of USDC. Using the more general pairName index 0 and pairName index 1 is a future-proof design. When we extend the DEX to support multiple pairs with multiple instances, this same logic will work for all pairs without any changes. Now, after each swap request, the DEX agent updates the trading pair's prices and K correctly. To keep the model easy to read, name the components clearly. calcAmountOut, call getAmountOut, transfer tokens. At this point, we have a fully functional DEX agent for swaps. It has its own core state. It has two key capabilities, calculation and execution. It exposes clear ports so that external agents can interact with it. And after each trade, it keeps its own data up to date. The game platform is ready. Now we can invite a player to make the very first trade and test whether our model works. Let's focus on the trader agent. We'll set its properties first, then behavior. First, set the trader agent type to population with an initial number of 1. We'll start with a single trader to get the simplest scenario running. Roles like trader are usually modeled as populations so that we can later simulate many users at once. Next, configure the wallet. For the trader wallet container, set keys ETH and USDC. Give them unlimited capacity, an initial amount of 0, and allow the amount to go negative. This last part is a small teaching trick. Being negative is not realistic, but it makes it easy to see net changes from 0 without insufficient balance interruptions at runtime. The trader's core behavior is simple. It actively sends swap requests to the DEX. In the goSwapIn process, after the start event, insert a call component named callSwapIn and an end event. This call component is where the trader will call the DEX's swapIn behavior. The behavior structure is now in place. Next, we configure the components inside the process. Set the start event to timer and turn on the active toggle. The trader should initiate trades. Set the timer so that at each tick, the trader swaps 1 ETH for USDC. This will give us a continuous dynamic process to observe. For the call component, set the owner to the DEX agent and target individual 1. Choose the swapIn behavior as the behavior to call. Now we pass data into the input ports. The trader's intent is swap 1 ETH for USDC, so set AMountIn to 1, token A to ETH, and token B to USDC. Notice you can't type a value into the trader wallet container port. Container ports expect the wallet object, not a number. Drag the trader wallet from the left panel into the process to create a local reference. Then connect a state connector from this reference to the container port, the small C icon on top of the call component. This tells the DEX's swapIn which wallet to operate on for this trade. Now all the ports are correctly wired and data can flow. At this point, all of the trader's properties and behaviors are configured, and our minimal model is complete. Now let's test and verify the behavior. First, switch the trader's wallet to monitor mode. Use the step button on the control bar to advance the model 1 tick at a time. Then watch the values in Trader Wallet and liqPool. You'll see that at each tick, the trader's ETH decreases by 1 and its USDC increases accordingly. In the pool, ETH increases by 1 and USDC decreases. This matches our logic perfectly. The flow of assets is correct. Now click Resume to let the model run through the remaining ticks. Let's look at the final data. In Trader Wallet, the ETH balance is -100. This confirms our allow negatives trick. It clearly tells us the trader has sold 100 ETH in total. In liqPool, the ETH reserve is 1,100, which is 100 more than the initial value. Asset conservation holds, and the logic is correct. We've completed our first basic scenario. One trader continuously sells ETH into a liquidity pool on Uniswap version 2. From the final numbers, we see that by selling 100 ETH, the trader receives about 335,000 USDC in total, so the average price is about 3,350 USDC per ETH, lower than the initial price. Finally, go back to the root canvas and configure the charts to visualize what just happened. When you plot K, you'll see that the curve is almost flat but slightly rising over time. The small upward drift is caused by the trading fees being added back into the reserves, so X times Y is slowly increasing. You can try setting feeRate to 0 and running the model again to see the difference. When you plot ETH price, you'll see a curve that is trending downwards. This is because the trader keeps selling ETH, increasing the ETH reserve in the pool. Given the rule, the relative price of ETH naturally falls. In the current setup, the price curve looks almost like a straight line because each individual trade is very small. So what happens if we increase the trade size? Now we'll try two simple ways of increasing trading volume. First, increase the amount per trade. Go back to the trader's goSwapIn process and change AMountIn on the call component from 1 to 10. Run the model again and look at the price chart. The curve now bends much more visibly. This reveals the nonlinear slippage characteristic of AMMs. As the trade size grows, the price change is no longer linear. This is a core feature of the constant product mechanism. It uses sharp price moves to prevent the pool from being drained. Second, increase the number of trader population. Change the initial number from 1 to 5. Run the model again. Now the price curve becomes even steeper and more pronounced. This simulates a situation where multiple traders are all trading in the same direction at the same time. The collective behavior amplifies price movements and gives us a clear example of how individual actions can give rise to a macro market trend. Up to this point, you have successfully built and validated a fully functional DEX model for a single trading pair, ETH and USDC. That's a big milestone, but real-world DeFi goes much further. A real exchange can have hundreds or thousands of pairs, and traders' needs are diverse. You could model each pair as a separate agent, but using the population mechanism is usually more efficient and elegant. Next, we'll explore how to extend our model from a single market to a richer multi-pair ecosystem. First, make a copy of the model and create a new scenario for multiple pairs. Go to the DEX agent's property panel and set the initial number to 2. Each individual now represents one trading pair, and you can configure them differently. Let's make the second pair USDC and WBTC with a pool holding 12 million USDC and 100 WBTC. To do that, we first need to make sure the liqPool container and the price variable support WBTC as a key. So go to the property panel for liqPool and add a new key WBTC. Then go to Price panel, switch the initial value method to batch construction, and add 3 keys, ETH, USDC, WBTC. After that, go back to DEX property panel and open the individual property settings pop-up. Click Add Property and add liqPool, pairName K, and price to the table. Now let's configure the two individuals differently. For liqPool, click the plus button next to its name, then add 3 rows. Choose ETH, USDC, and then WBTC as the keys in order. If WBTC isn't in the options, it means you skipped the earlier step. Add it to the key list and return here. Note that the order here is simply the order you added them while modeling. It does not have to match protocol level token 0 or token 1. Set the reserves as follows. For individual 1, set ETH to 1,000 and USDC to 3.7 million. For individual 2, set USDC to 12 million and WBTC to 100. Next, set pair name and K for individual 2. For pair name, use USDC and WBTC. For K, set it to 12 million times 100. If you don't override any individual specific settings, the system will use the default values for this individual. Finally, configure the initial price. Expand the price dict and add the 3 entries. For individual 1, set the initial price of ETH to 3.7 million divided by 1,000 and the price of USDC to 1,000 divided by 3.7 million. For individual 2, set the price of USDC to 100 divided by 12 million, and the price of WBTC to 12 million divided by 100. Now the second pair is fully configured. You can press the step button once to initialize the model and check whether the settings are correct. You may notice that for the liqPool container, the second individual unexpectedly has an extra ETH reserve. This happens because earlier we set a detailed configuration for liqPool on its property panel, which applied to all individuals by default. To fix this, simply remove the settings from the detailed configuration. Reset the model and step once again. You should now see the correct data for each pair. Here's a small reminder. When modeling, think early about whether an agent should be a single individual or a population. HoloBit does support switching between the two, but if you change it midway, you may run into default value issues or formula errors like the one we just saw. Thinking ahead can save you a lot of trouble. In the setup just now, we manually added keys for the containers. That works, but it doesn't scale well if you want to add many more tokens later. To make our model easier to extend, we'll use HoloBit's tag set features. A tag set is a list of tags. Each tag is like a named label you attach to each item. Tag sets keep token names consistent and give you autocomplete when you type. Now let's create a tag set. Click the New Tag Set. In the pop-up, give it a name, like ERC20. In the next input field, enter the token names that are tradable on Uniswap, such as ETH. Type ETH, then press Enter. Each time you press Enter, you add one tag. No quotation marks needed. Continue entering USDC, WBTC, DAI, USTD, AAVE, and so on. When you're done, click Create. You now have an ERC20 tag set, and you can add more names later via Edit. HoloBit also supports global tag sets. You can push your tag set in this model file globally so you and your collaborators in the same workspace can reuse it across files. Now let's use the tag set to speed up modeling. Go back to the liqPool Containers property panel and set the key source to the ERC20 tag set. Click Preview, and you'll see all tags in the set as candidate keys. This is much faster than typing them by hand, and it avoids name mix-ups like USDC versus USD coin. You can now delete the duplicated literal strings ETH and USDC, and keep only the ERC20 tag set as the key source. Do the same for the price variable with the ERC20 as keys. Also, set the trader wallet keys to the same ERC20 tag set. From now on, wherever it makes sense, input fields will show tag-based suggestions, so you can pick tokens quickly and consistently. Now that the second pair is ready, let's look at another common trading pattern. For the first pair, we built the mode where the trader specifies an exact amount of token A and receives an unknown amount of token B. We call this swapIn. There is also the reverse case. The trader asks for an exact amount of token B and is willing to spend as much token A as needed. For the second pair, let's imagine this scenario. A trader wants to receive exactly 0.05 WBTC per tick. How many USDC are required for that trade? We need to solve for AMountIn. The corresponding behaviors are getAmountIn and swapOut. In HoloBit, you don't have to rebuild everything from scratch. You can copy existing components on the same canvas or across canvases, and then adjust the details. Here, we have duplicated the earlier logic and created two new processes inside the DEX. Instead of walking through every click, let's focus on what changed and what you should pay attention to. First, look at getAmountIn. Conceptually, it is the mirror of getAmountOut. The main change is the direction of the key ports. AmountOut is now an input port, and AMountIn becomes the output port. Reserve A and Reserve B stay as inputs, just like before. The formula is the standard solve for AMountIn form based on the constant product rule and fee. Next, let's look at swapOut. Its structure is very similar to swapIn, but the roles of AMountIn and AMountOut are reversed. In swapOut, AMountOut is now an input port. The process calls getAmountIn to compute how much token A the trader needs to send in. After that call, the process writes the result into its own AMountIn port. The token transfer logic is the same as before. We still use a container operate component to move tokens between the pool and the trader's wallet. The directions, keys, and amounts are unchanged, so you usually don't need to touch the container operate. For both getAmountIn and swapOut, the start events remain normal, active off. They are still passive services on the DEX, waiting for callers to trigger them. Next, we configure the trader's goSwapOut behavior. Here, we also reused the existing structure and adapted it. There are two details that are easy to get wrong and worth highlighting. First, because the DEX is now a population of two individuals, we must call the correct individual when we trigger a behavior. In our scenario, we're interacting with another pair. To avoid hard-coding an ID of the individual, we insert a find component in front of the call component. Name it something like find pair, Set the scope to DEX.all, which means it will search across all individuals of the DEX agent. In the advanced options, add a pre-filter condition. This tells findPair to find exactly the individual whose pair name is USDC and WBTC. In the call component, set the owner to findPair. This means call the behavior on the DEX individual found by the find component. Choose swapOut as the behavior to call. Second, we have to pass the correct data for the process ports. AmountOut is now an input, and we set it to 0.05. Token A is USDC, and token B is WBTC. For the wallet, make sure the trader wallet reference is connected to the port. If you forget to connect this, the swapOut process will not know which wallet to operate on. The start event remains timer active on, just like goSwapIn. This means the trader will repeatedly request exactly 0.05 WBTC at each tick. Once goSwapOut is set, we update our charts. For chart 2, add a new data series for WBTC on the y-axis, because we are mainly interested in its price. Now run the model again and check how the data changes. After running, switch the data source for the chart 2 to the second individual, so you can see the price trend of WBTC specifically. The model file shown in this video will be published free in the HoloBit marketplace. You can find it there, download it into your own workspace, and inspect every setting in detail. In the next video, we'll continue building on top of this model and enhance the DEX's capabilities to handle adding and removing liquidity, and we'll model the behaviors of liquidity providers.